wanted to sort of go back and just look at a typo or something, just, I don't know, raise your hand, call out, and I can just jump back. So, okay, so title of this talk is Hacking the Visual World with OpenCV. So the visual world, what we see, it's nice, but we like to play games, have fun, and then do really useful things with it as well. So my name is Nicholas Dahm. There's too many Nicks in the world though, so a lot of people know me as either Dr. Nick or Aussie Nick. If you are going along with things, I probably advise you to just write down that GitHub address, because if you fall behind in code, you can also just look at the file there and catch up. So I'll just give you a sec to do that. So I'm a computer vision engineer at Trademark Vision. We're just upstairs at this co-working space, and we're working on image retrieval problems in the trademark space. And I'll go through some basic things tonight about what computer vision is, and then we'll go through a tutorial where we'll do what I hope is a fun app. It might be a little too soon or something for some of you, but gotta have some fun. So all right, let's move on. Okay, so we'll go through what is computer vision, and then a little tutorial called the presidential look. So if any of you watched The West Wing back in the day, there was an episode about the presidential voice. This will be about the presidential look. So what is computer vision? So it comes in a lot of forms and is used in a lot of different things. So top left, we've got basically some sort of UAV or possibly pilot control, just a camera. Probably someone's piloting a drone or something like that. Over here, we've got something which is rather cool. This is spectral imaging. So this is where you can get a special type of camera that can see more than we can see, and with finer detail than we can see. So it can look at, say, a piece of fruit and tell you whether or not it's ripe or not, regardless of how the color looks, that sort of thing. So really cool tech, a little bit expensive at the moment, but it's getting there. I don't know what the guy in the top right's doing. It's a NASA robot. I guess they're just getting onto humanoid robots. And this thing looks a little scary at first, but that's just face tracking, so you can tell if someone's smiling or that sort of thing. So all your phones are doing that already, so don't worry. Okay, so what sort of data do we have in computer vision? So for those that aren't really familiar with manipulating images or using them in their programs, basically up the top left here we have a mantis shrimp. I don't know if you guys know what that is, but that is something we should all be very jealous of, because we have 3 cones of vision, red, green and blue. This guy has 16, so he sees in psychedelic sort of colors. But anyway, so given that original image, there's a couple of ways we can represent it in a computer. So an image, as you probably know, is just like a matrix of pixels. And depending on how we want to look at it, so one way to look at it is convert it to grayscale. In this case, we get one 2D array of pixels where every value in the pixels is just a brightness value. And the other way is we keep it in the 3 colors, and just you have the red, green and blue color channels as 3 different matrices just sort of stacked together. And that's what an image is when you open it up on your computer. So, okay, so what sort of computer vision things happen? So a couple of the problems. So object detection, find me something, find the cars, find the faces, find my wallet. It's somewhere in this image but I can't see it. Object recognition, which is what is this exactly, this is used in the airport. You've got the new passport things where no one checks your face, the camera just looks at it. So that's a fairly recent thing that sort of got to the level where it can be used for something so critical. Object classification, trying to just decide what something is. This is becoming really big in a lot of places, so Google Glass and that sort of thing. That's sort of fallen in the background, but they'll be back and sort of tell you everything about a picture without knowing it. It'll help you search and that sort of things where it's really going to shine. Image matching, obvious. Image retrieval, so you've got an image of a car, but you want more images of cars that look sort of the same. So that's what image retrieval is. Object tracking, that's the scary one, where they can track you from security camera to security camera and follow you all around the city. But it's got good uses too. Scene reconstruction. Now this is something really cool. There's a lot of work being done on this, so you can take video or even a few still images of a scene and you can create a 3D model from it. And then if you want, you can alter the 3D model and re-render it back into video or stills with the content you added. So essentially you can change a video scene, and it's really cool when you see it in action. So YouTube it later if you feel it. And the other one is image restoration, so removing wrinkles, that sort of thing, fixing up the contrast, you know, the lights turned on just as you took the photo. Most of this is done automatically on your cameras, you don't notice, but yeah. So this is our thing, Trademark Vision, we're image retrieval. So this is sort of how it works. You get an image up the top like that, that's the AT&T logo, and then we search through trademark databases from around the world and look for anything that looks visually similar. So some of these are a little bit different. You know, these ones here, they've got different kind of swirls. No, that's actually a really good result. Should have found that. But you get different things, and this helps us find things on the internet, things like that. There's Google reverse image search for the generic web, but essentially if you want to find something, you've got a picture and you're not sure if it's copyrighted, you can do a reverse image search on it, search the internet, find where the source is and determine whether you're going to get sued or not, that sort of thing. So how do we do any of this? You know, how do you sort of look at images? And I mean, the pixel values themselves are so random, you can't really say is this equal to that unless they're absolutely identical. So what we usually do is we get some sort of descriptor, some way of describing the image in terms of a way that's a little bit more generic. So this is the histogram of oriented gradients method, so or HOG for short. Basically, it's a little bit hard to see up here, but given these input images, what it does is it looks at pixels, and when one pixel is different to the one next to it, there's a gradient change between the two. And so what you're seeing here is the gradients of our logo and the gradients of another magnifying glass. And then comparing in this space is a lot cleaner in terms of the maths behind it, because you know at some level we're going to do a mathematical comparison, and if you do it at pixels, you're just going to have a bad day. So things like this, you look for these descriptor techniques when you're trying to compare images. This is essentially what you do with it. You shrink it to the same size, and then you just grab essentially all the gradients out into some big long array, take a difference, and take like an L1 distance or that sort of thing. And you come up with a similarity score, or in this case a difference score, between the images. How similar are they? So that's just a short thing of one of the ways you can do computer vision. So in Python, we've got a few tools that are available for us. OpenCV is the big one, at least if you're starting out. So it's something that you can grab off the shelf, just plug in, start typing things, and away it goes. So it's got tons of algorithms, a lot of them really cutting edge, only a year or two old, some of them. It's fairly fast, it's been around for a while. It's fairly stable, depending on who you ask. And in the Python interface, it uses NumPy for like storing the images, which makes it really handy to just sort of integrate with anything else you're doing. And there's the Python imaging library is like the default Python thing. So it was sort of around before. It wasn't intended for computer vision. It was intended for showing images, resizing them, just the very basic things. But it's got some really clever little operations that you might want to do. And there's a very easy way to translate from a NumPy array to a pill array. So between essentially what OpenCV wants and what pill wants. So you can use both. All right. So let's get started. We've got a lot of code, so I'm sort of trying to keep the pace a little bit, but do let me know if you fall behind, because I think it's quite fun. So I hope anyone who's following has Python, OpenCV, and NumPy installed at least. If you can't import those now, it's probably going to be a hard time unless you've got Linux. If you've got a Mac, it's a little bit hard, and if you've got Windows, it's really, really hard. So yeah. Mac's getting better, actually. I did brew today, and it was quite clean. All right, so here's the first part of it. So basically, in this, all we're going to do, if you follow that Google URL there, you'll get this exact squirrel. That's kind of important for something later, which will be quite fun. So import CV, obviously that's the... So OpenCV is on version 3 now, which is really confusing because you import CV2 now, still. So in version 2, they changed it from import CV to import CV2. In version 3, they kept it the same. I don't know. You can call it an API level or something like that. So basically, to load any image, just cu2.imread, in it goes, and then as any NumPy thing, you can do the shape. And so it's 140 pixels high, 160 pixels wide, and it has 3 color channels. So it's a RGB image. And so that's just sort of how you read one in. This is how you show one. It's really simple. Just cv2.imShow. Give it some sort of name. This doesn't matter. It's just an identifier that'll come up on the window. And then pass in the image to show. If you want to do the grayscale version, you can easily convert between any kind of... So in OpenCV, there's tons of different image formats. There's RGB, there's grayscale, there's BGR, there's HSV, HSL, HSI. There's tons of them, but the main ones you have to deal with is BGR and gray. So we always talk about RGB images, but for some reason, and there's a long history reason for it, but a lot of things do BGR instead of RGB. Makes it a little bit more annoying to remember, but if you ever show an image, you'll instantly know if you got it reversed because you'll get really psychedelic colors. And then once you convert it, if you print the size again, you'll just see 140 by 160 because it's only one channel on the third one, so NumPy just doesn't show it. Cool, and so essentially, you should have a couple of windows like this. So I'll just switch back to this. A little bit small to see, but oops. They'll probably be, depending on your computer, they'll be on top of each other, but you should end up with 2 windows just like that. The wait key operation here, it's commented out in this file, but ignore that. This is important. It waits for you to press a key, but OpenCV won't actually show you the windows unless you call that. I'm sure there's a way around it. You can do a wait key with like very small things like 0.001 and it'll probably work, but yeah, essentially that's it. So does anyone need me to hold on? No? Cool, cool. All right, back to it. All right, so we've got a couple of images showing. Let's do something a little bit more fancy with them. Firstly, for anyone who just wants to know about it, if you are using pill images or want to get a pill image for any reason, this is the simple conversion. So there's a NumPy function, asArray, which takes a pill image in and gives you back a NumPy array. Because pill does RGB images, you convert the RGB to a BGR. Nice and simple. If you want to go back the other way, convert it back to an RGB and use image.from array from the pill image library. So it's fairly consistent, and so definitely use both if you want to do it. So, all right, let's see something more interesting than just a squirrel. So now let's look at ourselves, because we're all vain. So this is the way you display a webcam or any other camera connected to your computer. Nice, easy thing. So cam, just some variable, cv2.video capture 0. So it's saying video device 0. I think it's usually at /dev/video 0 or something like that. But all the cameras that are connected to your computer will get enums 1, 0, 1, 2, 3, that sort of thing. And so usually 0 is the first one. Go with that. Then you read a frame from the camera. So cam.read. It returns, basically the ret is a did it work or not option. So if for whatever reason the drivers in your MacBook or whatever, you're running Linux and the drivers are bad, you'll get a false instead of a true for the ret. And frame is just a NumPy array like we were talking before with the actual image data. And then just, this will help you see what your camera's resolution is. For some cameras, and this was only a problem for me today because my home computer's got a terrible one, you may need these 3 lines here. So for this MacBook Pro that I've grabbed, it's got a really high resolution and it almost goes off the screen and makes everything really ugly. So 3, 4, and 5 are the width, height, and frame rate. So you can set those if you want to just downscale. Cool. And then basically we just loop through because we want to keep getting frames. Grab a new frame each time, show it in some camera window, and then we do a wait key of 1, which says, see if anyone presses a key in the next 1 second, and then it returns that key. It returns -1 if they didn't press a key. And so all this does is if you do press a key, it'll just break out of the while loop and end the program. Otherwise, it'll just keep looping around and giving you new frames. And so you'll see yourself like this. So yeah, doesn't really do much, but you know, if you ever don't have a mirror and you need to check if you're, you know, spinach in your teeth or something, yeah, cool. All right. Okay, so we did lose the squirrel, and I like squirrels, so let's get him back in there. But we don't want to lose ourselves as well, so we're going to merge the two together. We're going to put the squirrel into our little world here, into this room. So there's a little bit of, let's say, boilerplate code for the moment. So this, essentially what we're going to do is we've got the squirrel picture, and as you might remember, the squirrel has a black background. Now that's important, it just makes it really easy to get rid of the background and make it transparent. So that's all we're going to do here. So this, basically the very top thing is the squirrel gray, which we created before by converting the squirrel image to grayscale. So that's just a NumPy array, just a 2D matrix. And basically you create a mask from that and say, if the pixel value is 0, then you get a false, and if it's true, sorry, if it's greater than 0, then you get a true. And so you get a big Boolean matrix of trues and falses, where the trues are where the squirrel is and the false is in the background. This next operation, which creates the mask, essentially all it does is it makes it a three-channel image. So you've got the one-channel Boolean matrix, but you need a three-channel one so that you can essentially combine it with the. Sorry, I'm explaining this bad. So there's the original squirrel image, SQ. That's a color image, and so it has dimensions of 160 by 140 by 3. And so when you tell it what you're going to mask, this has to have the same dimensions as that. And so you need to say that you're going to get the red, green, and blue channels for the squirrel parts. And so that's why we create, you know, VVV, which is like true, 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 or false, 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 for every pixel, just 2 for loops together. Do you guys know list comprehension, yeah? All pretty standard? Yeah? Cool, okay. If anyone doesn't understand list comprehension, feel free to ask or anything. It's incredibly powerful, and if you're doing computer vision, it is kind of necessary. Doing these sort of operations in real time, you know, 15 frames a second or higher, is really, really expensive. So people walking upstairs. Okay, so what we do is after we get our original frame, we copy the squirrel image. This is the source, and this is the destination. So what we're going to do is we're going to copy the squirrel image to, this is where you set the range, so you're getting the frame at the height of the squirrel from the bottom. So images, the 0, 0 coordinate is in the top left. And so basically we've got an image like that. We want the squirrel to be down here. So we go back from the top, essentially from the highest value up the height of the squirrel, and take down to the bottom of the image. And then we take from 0, which is the left for the width, across the width of the squirrel, and then we take all 3 color channels with this, and yeah, and we mask it. And what we end up with is a little squirrel in the picture. And it doesn't change anything, the video still works exactly as expected, except we have a little friend. Nice and simple. I think this was about 10 years ago on phones. They had those little photo booths, and you'd go in and they'd have a little thing and you'd take a picture, and you know, teenage fun. Cool. So we got our little squirrel friend. Okay, so let's do something a little bit more fancy. So we need to give ourselves a presidential look. This was the whole thing. I mean, squirrel's nice, but we've got to make ourselves look a bit better. But the computer doesn't know what's us and what's a background. It knows that this is red, this is green, this is blue, this is white. It doesn't know what a face is, anything like that. So we have to sort of tell it that this is me, this is what I want to change. And so essentially we're going to employ face detection here. So it doesn't care who you are, it's just going to detect the face. It's actually not true. Computer vision algorithms are generally very racist. So the algorithm configuration that I have in there may not work for you if your skin color is different to mine, or you don't have as much beard, or it can be very finicky depending on what you've got. There's some great stories of this happening in practice. The Kodak camera that asked if people blinked wasn't always very PC, shall we say. Okay, so what we're going to do is use something called HAR cascades. And so essentially it's going to look all through the image and try to find things that look roughly like a face. I'm not going to go into exactly how they work, but all you need to know is that essentially it scans through the image and looks for things that look like a face. It doesn't matter whose face or anything like that, but it'll detect faces. And this part here is not racist. We'll get to the part that's racist later. So somewhere on your computer, they'll probably, or if you've installed OpenCV, this file will exist. So on my home computer, which is running Archlinux, it was located in user share OpenCV HAR cascades. But on a Mac like this one, when you homebrew it, it's in something like that. So you'll need to get the location of where these HAR cascades are. So if you've homebrewed it, that's where you want to look. User local seller, OpenCV3, etc. Share OpenCV. So this tells it what kind of detector to use. And so we're using the frontal face detector. So you can get like dog detectors, cat detectors, any sort of detectors. I mean, they work really good on things that are straight on. So faces are sort of a perfect example. But yeah, so there's other ones. And if this one doesn't work, there's an alternate frontal face thing, and there's probably a side face one. And then all we do, we get a gray version of the frame because this algorithm works on grayscale. It doesn't need or use the color channels. And then we just go for that cascade. Sorry, I've just sort of split this code up so that can go outside the while loop. Only need to do that once. Only want to do that once. And then inside the while loop, after all the other code, just before the break and wait key and that sort of thing, just dump this code. So essentially all it's doing, getting the cascade classifier and detecting across multiple scales, because we don't know how close someone is to the camera, they might be right up in it. Don't worry about what any of these parameters mean. It's sort of boilerplate for now, and it probably wouldn't do much good to learn unless you really want to get stuck into it. But those are sort of default values, and they'll generally work. So yeah. Okay, so we've detected the faces now, but it hasn't essentially done anything. It's got a list of faces. So this returns a variable called faces, and it's just a list of XY, the starting point, and the height and width of the face. So we need to make sure it's working, essentially draw it. So this looks a little bit confusing. This is for the benefit of something later. So it's kind of optional. That line there is necessary, but you could skip all this if you want. This is how we essentially draw a rectangle to bound the face. So just cv2.rectangle, give it an image, give it a starting coordinate and an ending coordinate, as in a top left and a bottom right, and tell it what color. So 02550 is green, and I think the 2 is the thickness, 2 pixels thick, the box we're going to draw. So all I've done here is, for something later, the box that we start off with is about that big. And so it doesn't really cover the whole face. As you turn, it only gets a little bit of it. And for what we'll do in a minute, it doesn't look as good. So all this does is saves the original values, just in case we need them later, and then it just extrudes it. So the height goes up a bit, the width goes out a bit, and it just moves it over. So you've got a box that generally encompasses the whole face. And then I've drawn that one in, what is that color? Yellow, blue and green, I think. Yep. So you should now have this face detector. So now you can see, and you can easily fool it, anything that looks like a face, but it'll follow you around. I think it does multiple people. I don't want to pull out this cable, otherwise I'd turn around my MacBook, but yeah, so as you can see, the green box is kind of short. As I turn to the side, the green box, it's still there, but it sort of misses a lot of my face, so I've made the yellow one to be a bit bigger. But we'll get to the fun reason why in a minute. Alrighty. Okay, so now my skin's not very presidential. doesn't, it's just an average Joe Blow sort of skin. So we're gonna modify it a little, make it look a little better. So essentially what we do here is inside that yellow box that we drew, we're going to look for anything that looks like skin color. So skin color is very hard to describe. I guess mine's some sort of creamy something. I haven't been out in the sun much, so whitish cream. So the first thing we do is we convert it into a different color space where you can essentially view it better. I should have brought a slide on this. Let me just pull this up on Safari. Sorry, I'm not a Mac user. There's a good image down here. Okay, so in terms of RGB, it's very hard to define. So in terms of RGB, can you try and think of how you describe a face? Like how would you say a face is within this like this sort of red and this sort of green and this sort of blue? Like how much red, green, and blue is in a white-looking face like mine? It's essentially a very bad way of looking at it. So the solution is to put it into a different color space where we can separate the different components. And so this is I think the most important one, or the easiest one to sort of get to learn. It's called HSV. There's that easy conversion, BGR to HSV. You can do it to any image, and it'll give you back another 3-channel image, but instead of BGR, it's HSV. Now the hue is essentially the color. So in one of those channels, you have what color you're looking at. Another one is the saturation. That's how strong it is. So, if it's very blank, like, probably my skin is, then it's got low saturation. If it's like a very strong color, it's got high saturation. And the last is value, which is a bright to dark sort of thing. So if it's closer to a black color, then it's low in value. If it's closer to a white color, it's low in saturation. And then the hue can just decide. So as you can see from this, for a skin like mine, you could say that maybe cut the pie here and up there in that yellow section, and I think my skin's probably somewhere in that sort of range of the value, and I'm not sure about the saturation, somewhere in the middle there, but this allows you to essentially pick and choose the colors you want out of an image and find things that you couldn't otherwise find just using red, green, and blue. Okay, so we take a frame, and then we take essentially a sub-box of where the face is. So this is just saying, for the coordinates where we found the face before and drew that yellow box, just take that part of the HSV, and then we have this min and max values. So this is my very rudimentary expression of describing my skin color. So it's between 0 and 200 hue, which is a very large range. It probably could be turned down a little bit. Between 0 and 120 saturation, and between 40 and 200 value. Now, this is in the range of 0 to 360, I believe, and this is in the range, these two are in the range of 0 to 255, which is, a little bit confusing at times, but essentially you look at it and you play with it. So when I got here just now, I realized that the values I had didn't work because upstairs is a little bit darker than down here. And so I had to change the value to be 110, otherwise it grabs everything, because if you look in the background of this, you'll see that there's a light shining down on me from above and everything's a bit white up there. So in order to just get my skin color and not get all the background, I've had to sort of tailor it to the scenario. So these methods are very good in processing plants and that sort of thing. So you've got some sort of assembly line and you just want to detect where the objects are. Very controlled environment. If you're going to go into outdoors or anything, you'd need to use something better. But I wouldn't be able to do it in a talk. So this is a little bit of NumPy magic, essentially. So all it does is it says, find everything within the range that's inside that. So it gives you another one of those true and false matrices, which has anything within that range true and anything outside that range false. So now we've got essentially the segmented face as opposed to the background. And then what we can do with that is give it a little bit more presidential color. And so I've defined these three essentially operations to do to the three different parts of the, like to the red, green, and blue of the original, or the blue, green, and red of the original image. So if you multiply the blue channel by 0.2 and the green channel by 0.65 and the red channel by 0.7, then you get this more presidential color, which will come up in a second. This here, all this does, is just make sure we don't get above 255. So all the numbers that we generally deal with will be in the range of 0 to 255. If they go outside of that range, they loop around and you come up with really strange looking things. But you can usually instantly know that that's what you've done, because you'll just come up with a whole lot of white or black or red or green in the middle of just nothing. So, and then we convert it back. So this NumPy minimum essentially will give us an int, and then we just need to force it back to a uint8, which is an unsigned integer with 8 bits. So just in the range of 0 to 255, which is generally always what you use in computer vision. Brightnesses, color strengths, that 0 to 255. And then what we do is we copy the new face color onto the pixels that were detected as face color for the last one. So we've got that face in range mask, which said these are skin color pixels, and then we just copy that over. And what we end up with is a more presidential color. I know, it's been in the news enough. You guys probably don't want to hear about it more, but I needed a topic, so yeah. Unfortunately, the background's still a little bit playing with me, but you can roughly see it follows most of my skin pixels. If I had a darker background, it'd work a little bit better, but cool. Alrighty. There's one thing missing. What's missing? Anyone want to take a guess?
The hair.
The hair. The hair is missing. We need some presidential hair now. I don't want to bother downloading any hair, so we'll ask our little friend the squirrel to donate some. So we're going to take some hair from the squirrel. Essentially, the squirrel is it's an image as well, so we can just segment it. So what we're doing is we've got the squirrel image. We're taking from 30 down to the very bottom, and from 0 to 70 pixels that way. So we're getting the bottom left of the squirrel image, which will be the little taily part. Then we're going to rotate that on its side, so that can fit on top of my head. And then hair mask. What is hair mask here? I can't remember. It's the mask we had from before. So we previously masked the squirrel pixels so that we could copy just what's the squirrel and not the black background. And so we still need to use that mask when we're moving it anywhere, otherwise it will move it with all the pixels it currently has or all the pixels it originally had. So we get the exact same part of the mask, and then we rotate the mask so that we've got two things identical. We scale it to be, the yellow box was like this, and so we just want it to be just on the top of the head. And so I've sort of used the original dimensions that we had of the width there. And then we resize it so that it's in this scale, and so it'll just move it, and it is very basic maths. You get the width that you want and the width that you've got, and then you guys know all that. Cool. All right, so now to put it on our heads, we've got the hair mask. Ooh, sorry, did I duplicate that? Right, sorry. The hair mask wasn't a duplicate, so that's just turning it to that and scaling it as well. I just split it up to 2 slides because it's a little bit big, but essentially we're doing the exact same thing to the hair mask as we were to the squirrel mask. Okay, so basically we turn it into another Boolean array, and then down here we do another wear hair mask, essentially moving the squirrel, twisting him. And this is just something I've done to lighten it up a bit, because the squirrel's tail's a little bit brown, sort of a little bit too dark, you know, not very presidential. So this little check here is a common thing that you'll need to do. So one of the things that often happens in computer vision is you'll go outside the boundaries of the image. And so if you try to copy something to the outside, obviously it's going to crash. And so often you'll find that your code has a whole lot of little range checks to make sure everything's still going to work. And then when we add that, we get a presidential hair. And so there we go. The presidential look, everyone. Let me see if I can turn it around and see how many there we go. Look at all these presidents. Brilliant. Alright. Well, thanks for coming to my talk. This is my first one, so I'm not sure if I sped through it way too fast or way too slow. But thanks for coming along. If you guys have any questions for me personally, want any help with computer vision stuff, there's my GitHub, LinkedIn. That's my Meetup thing there. I think my name is Dr. Nick on Meetup, so you can just catch me there. And if you really like computer vision, we are actually still hiring people. So if you're an intern, or we also need some just general people to help out with the team. So if you like the idea of computer vision and you want to work closer to it, let us know. We're just upstairs here and always happy to listen and see what people want. All right, thank you guys.